afternoon, everyone. Welcome back to the course, Computational Method on Optimization. Today, we will continue the topics on constraint optimization. And we are going to discuss a method which is called Newton method. Okay, let's review a little bit what we have discussed before. We have discussed the gradient descent method. Okay, it's the first order method to minimize unconstrained problems. Okay, fx, if we assume f is differentiable. Another motivation of gradient descent method is from the first order Taylor approximation. Okay, if you have seen my lectures before, I have introduced the gradient descent method in the sense of monotone inclusion problems. Okay, it can be related to the proximal point method, but another way, which is more usual, I mean, for the introduction of gradient descent method, is to consider about the first order Taylor approximation. Okay. Since f is differentiable, so you can have this kind of approximation. So what we want to do is we want to minimize this approximation. Okay? So here we can use cos C Schwarz inequality. Okay? Because you have inner product here. Okay? You use the inequality for this inner product. So and you have an upper bound and a lower bound, and you can reach the lower bound, the inequality. The equality when you take x minus xk equals some alpha times the gradient. Okay, then you get the minus gradient direction. Okay, so this is one way to understand the gradient descent method. Okay. So we need one preliminaries for Newton method, okay, especially for the analysis, convergence analysis, which is a spectral norm. Okay, the spectral norm of metric is measures the maximum increase in Euclidean norm, which defines the spectral norm of a matrix A is the maximum of AX, norm of AX, because here is a vector, so it's a two norm, okay, over 2 norm of X. And we have several conclusions, but we give the conclusions here without proving. Okay. For example, if A is a symmetric metric, the spectral norm of A is equal to the maximum of the absolute value of any eigenvalue of A. Okay. And another is if A is a symmetric and the norm, the spectral norm of A is bounded if and only if the norm vector of A belongs to the negative C and the positive C. Okay, so we have these two conclusions we will use later in our proof. Okay, so let's go to the Newton method. So we just mentioned the first order method can be regarded as minimization of the first order approximation. So if we assume here f is twice differentiable, and then we can have the second order Taylor approximation of f. So we can have this approximation. We have one more term, okay, it's a square term related to the Hansen matrix. So what we want to do is we want to minimize this second order approximation. Okay, so what should we do? We regarded the right hand side of this approximation, this part, we regarded this part as a function of x. Okay, then we minimize it. How do we minimize it? We just set the gradient of this part equals 0. Okay, so we take the gradient of this function respect to the variable x. Then we get this. We get this equation, and then we want to solve the x. Okay, so you put the gradient on the other side, and then you need to multiply by the inverse of the Hansen. Okay, so you get this inequality, and then we can get the pure Newton method, which exactly, sorry, it's a typo here. This should be xk plus 1 equals xk minus the inverse of the Hansen times the gradient, okay? And of course, sometimes, because here we do not have step size, okay? It looks like we do not have step size, but the step size equals 1. If we want not a fixed step size, okay, we can give a step size like eta k. It's called damped Newton method. Okay, so the key point of the Newton method is using the second order approximation, and then you minimize it, and then you will get equation. Okay, equation. It's a non-linear equation. So the key. What you really need to do is solve this nonlinear equation, okay? Remember it, we will mention it in the later slides, okay? So the key point here, we need to solve this nonlinear system, then we get the pure Newton method. If we have step size which does not equal to 1, we have this damped Newton method. Okay, so before we give a geometric interpretation of Newton method, we go back to the steep descent, okay, which is gradient method. We choose here we have a point x, okay. This is a gradient, which is which along this direction your function value will increase, but along the inverse, which is the negative, the minus gradient, your function value will decrease. So the gradient method is you go along this negative gradient and with some proper step size rules, okay? But the Newton method is different, okay? For example, if you x1 have x1 here, and then you get x0 has here, you get x1. But how do you get x2? Remember, how do we get the Newton method? We use the second order approximation, okay? I will write it here. So if your f is twice differentiable, and then you have this fx, have this second order approximation, okay? And you have a second term here, 1 over 2 xk, the Hansen fxk, and x minus xk here. Okay, so this is a quadratic function with respect to variable x, okay? If we assume this is posi-definite, okay, this function is a positive quadratic function, okay, and the corresponding graph is the ellipsoid, okay? So that's why here we have an ellipsoid, or you can call it, or it's the quadratic approximation, okay? You have this approximation which is ellipsoid, and then you minimize this. You minimize this quadratic function which is ellipsoid, and then you get x2. Okay, so this is different because in in the gradient descent you go along the negative gradient. Okay, but in the Newton method, you have a point xk, and then you do a quadratic approximation, which is ellipsoid if the Hansen is positive definite, and then you minimize this quadratic approximation, and then you get next point. So you have a first one ellipsoid here, you minimize it, you get x2, and then you have another quadratic approximation, which is also here is ellipsoid, then you minimize it, you get another point. Okay, so this is a difference between the Newton method and the gradient descent method. Okay, so first we will discuss a property of the Newton method, which is called a finely invariant. So we consider these problems. Okay, we have a transformation y. Okay, we do a transformation, we get transformation, and we get a new problem. Okay, which is minimize the function gy, which is first you do the transformation, and then and then composition with f. And for this function, okay, we have two problems. One is f, another is g after the transformation. The very interesting property of the Newton method is if we use if we use Newton method for both these two problems, we have the similar result. Okay, we have the corresponding iterates. They are connected by the same transformation. Okay, let's see how does it means. What does it mean? So first, we need to calculate the direction of the Newton direction of the function with respect to g. Okay, so we need to calculate the inverse of Hansen with respect to g and times the gradient of g. Okay, so by the computation, you can have finally the A inverse and the A inverse and the minus the gradient of the Hansen of fx inverse times the gradient of f. And we can see clearly this is just the Newton direction of dx. Okay, so we get the conclusion. The difference between the direction of dx, which is the Newton direction of respect to f, and the Newton direction of dy, which is respect to the function g, which are connected by the same transformation, okay, but without b. And if we assume we have a point x, which are corresponding to a y plus b, okay, and we assume next iteration will be x plus equals to x minus some step size lambda times the Newton direction dx. Then by the computation, we can have x plus equals to x minus lambda dx, and we substitute the x by the a y plus b, okay, and then we can substitute, and by the conclusion we just got here, okay, and the dx are corresponding to a dy. Then we get this equals to a times y plus minus plus b, okay. So this means if your current point x is related to the y by the transformation, okay, then the next iteration will be the same, connected to y plus by the same transformation, okay. So this means even if you scaling your problems, if you still use the Newton method, your iterates will not change if you choose the same initial point. But the gradient descent method will not have this property. Okay, this is what we call a finely invariant. And another interesting about the Newton method is sometimes it fails. It is not very stable or robust like the gradient method. This is an example which I get directly from the reference, which I will give this reference at the end of the slide. Okay, so we can see here we have a function. Okay, the graph is like this, and to implement the Newton method, we need to calculate the gradient and also the Hansen. Okay, the experiments here is like this. We have two initial points. Okay, x0 equal to 0.5, another is 0.7, okay, and the author here test both Newton method and the gradient descent method. Okay, here the gradient descent method with a fixed step size 0.1. Okay, so here the first table is with the initial point x 0.5, and the table the right side table is the initial point x equals 7. Okay, we can see that if we use an initial point which is x0 equals to 0.5, the Newton method converge, and compared with the gradient method, it converges very fast. Okay, it converges very fast. And on the other hand, if we use another initial point x0 equals to 0.7, unfortunately, the Newton method diverge. Okay, it's diverge also very fast. Okay, but on the other hand, the gradient descent method will also converge. So this is the drawback of the Newton method. Okay, which means it is which says the Newton method is very sensitive about the initial point. For example, we can see the global minimizer of this function is 0, okay? If you choose 0.5, which is somehow closer to the solution, you get converge. But if you choose a little bit further, for example, you choose 0.7, then you got diverge, which means you choose a point which is not close or not close enough to your solution. You will diverge. Okay, so this is one of the drawback of the Newton method. Here is another example of the divergence of the Newton method. Remember, the key point of the Newton method is to solve a nonlinear system. Okay, let's go back to the blackboard. So the Newton method is to minimize. Okay, we want to minimize this. We want to minimize this second order approximation. Okay, later we get this one, the gradient of fxk plus the Hansen times x minus xk. Okay, so the key point is to solve this nonlinear equation. So somehow in some textbooks people study the Newton method by studying the Newton method for solving nonlinear system, okay, because in some senses it's more general than the minimization problem. But anyway, in this graph we can see, if you choose a point, this is a function, okay, this is a graph, the curvature of the function, graphs of the objective function. If you choose x0 here, and then you get x1 here, and then you get x2 here, and then you get x3 here. So it also diverge, okay, it's also diverge. But when we also, since even if Newton method is not very stable or not robust, sometimes it diverges. But when it converges very fast, okay? It's a quadratic method. So first, we will discuss the good points of the Newton method, which is local convergence, okay? Before we go to the local convergence, we need something like a Newton method lemma. Remember that when we discuss the convergence of the gradient method, we have the gradient descent lemma. But here we have a Newton method lemma. Okay, it says if f is twice differentiable with an invertible Hansen. Okay, since you need to define the Newton direction, you need the inverse of the Hansen. It's better to assume it's invertible. Okay. And we also assume x star is a local minimizer or local minimum of f, and the distance to the optimality of the iterates by the depth Newton method, which means you have the step size, okay, no matter whether it's fixed or not fixed, but which should be greater than 0, which satisfies this inequality, okay, where we have the definition of hk equals like this. Actually, if you delete x star on both sides of this equation relation, you just recover the Newton method, okay? So let's say how to prove this. This is quite simple. The idea of this proof is we write second order direction, okay, as the Hansen matrix on the line segment which connecting the x star and xk. Okay, so this is somehow the Hansen matrix, the Newton direction without the inverse, okay, without the minus. So you have this equals to, here you have the gradient of x minus the gradient of fx star, okay, because we already assume that x star is a local minimum and f is twice differentiable. So you can use the necessary condition, okay, of the unconstrained problems, okay, because this is 0. And then we can rewrite this part as the integral from 0 to 1, and by the Hansen matrix, okay. And then we rewrite it like this, and then we will get hk, okay. Just use the first order necessary condition. And then by the definition of this integral, you get this equals to hk, okay? And then you rewrite, okay, since this is minus, sorry. This should be xk plus 1 minus x star. so it equals to xk minus x star. Here, in the first inequality, we just substitute xk plus 1 by the definition of the damped Newton method. Okay, so this is a Newton step, Newton step, and then you have this just by the definition of hk you got here. So this is quite simple. Okay, so before we go to the local convergence, so let's imagine what we need. Okay, by the encounter example here. By this counter example, we can conclude that if initial point x star, which is not close enough to the solution x0, the method may diverge. On the other hand, which means your initial point should be close or close enough to your solution. Okay, so here the first assumption is you have a point which is close. You have your initial point, which is close enough to a local minimizer of f. Okay, and then you have this strong curvature at the solution. Okay, so at your solution, your gradient should be 0, of course, and the Hansen at the solution should have the minimum eigenvalue, which is greater than 0. Okay, you have the minimum of the eigenvalue of Hansen at the solution should be greater than 0, which means you have somehow positive curvature. And we also need to assume the function of the Hansen is the L smooth, okay, or it's Lipschitz continuous of the Hansen. Okay, so the conclusion is, so before we go to the conclusion, we need this somehow. This should be a lemma, okay, or a theorem, but it doesn't matter. Under the assumption of strong curvature and M smooth assumption, okay, what is a strong curvature? It means your Hansen at your solution should have a positive minimum eigenvalue, and your Hansen and M smooth means your Hansen. The Hansen matrix should be M Lipschitz continuous. Okay. Then the spectral norm of this matrix, okay, and which xk is generated by the Newton method, satisfies this inequality. So the matrix of I minus hk, the spectral norm of this matrix is less than this m over mu xk minus x star. Okay, and what is mu? Mu is the minimum eigenvalue of the Hansen at the solution. Of course, we assume that the Hansen here is symmetric. Okay, then the mu is the minimum of the eigenvalue of the Hansen. Okay, whenever the distance between the xk and the x star is bounded by this constant. Okay, is bounded by this constant. We need this to prove the convergence of the local convergence of the Newton method. Let's see how do we prove it. First, we rewrite this. Okay, we rewrite this matrix. We rewrite the the identity matrix in this form, and then we can put this inverse outside of the integral. Okay, so we have this, and then we taking the spectral norm on both sides of this equality. Okay, then we use the inequality about the integral. Then we have this. This says the spectral norm of the I minus hk is less than the spectral norm of the inverse of the Hansen times this integral. Okay, but here we already know, according to the assumption, we know Hansen is Lipschitz continuous, so we use the Lipschitz continuous of the Hansen here. So we have the m 1 minus lambda and xk minus x star, which is norm 2. Okay, So this integral has nothing to do, this term, we can calculate the integral with respect to lambda very easily, okay? So we get this term equal to min m over 2, the spectral norm of the inverse of the Hansen times the xk minus x2. Okay, so remember we have an upper bound of the Hansen, not Hansen, but I minus hk. On the other hand, we began from the M smooth. Okay, we began from the M smooth assumption. This implies this matrix. Okay, this matrix has the minimum eigenvalue of this and the maximum eigenvalue of this. And in particular, we can have this gradient, this Hansen, can be bounded by this part, this inequality just directly from this one, okay? And then we know that because here you have the Hansen at the solution, we assume you have the strong curvature, which means at the solution, your Hansen has a minimum eigenvalue, which is mu. Okay, so you have this inequality. Just use the assumption about the strong curvature at the solution, and then you have this, which means the Hansen has a minimum curvature, minimum eigenvalue at xk. Okay, at point xk. So we have this. Okay, so we can actually. This conclusion, okay, this conclusion is from the previous slide. Okay, it's from previous slide. So together with this inequality, no, sorry. There is a problems here. Okay, there is a problems here. Okay. Okay, so we have a lower bound of the Hansen, and we have sorry. Here is the inverse. We know the gradient, the Hansen of f at xk has a lower bound, which is mu over 2, which means the minimum of the eigenvalue is mu over 2. But the inverse has the maximum eigenvalue of 2 over mu, okay, because we have the inverse here. So this inequality immediately from this one, but we take the inverse here, okay. So in particular, the spectral norm of I minus hk is less than 1 over 2. Okay, it's less than 1 over 2. But why? First, we have the upper bound of this inverse. Okay, and in the last slide we have the norm of I minus hk is bounded by this constant, the inverse of this or the inverse of the Hansen, and xk minus x star. But we already have another upper bound of this inverse of the Hansen, which is 2 over mu. So we can have the I minus hk has an upper bound of 1 over 2. Okay, with the spectral norm. So together with the Newton lemma, what is Newton method lemma, which says xk plus 1 minus x star is I minus the step size eta times hk times xk minus x star. Okay, so we know the distance. To decrease exponentially, because we know this has an upper bound of 1 over 2. Okay, so by the theorem we have analysis here. And we can also conclude that the distance decreases double exponentially. Okay, double exponentially. Why here? Because okay, here you have this one. Okay, you have this one, and then you put this together with this Newton method lemma. Okay, then you have this one, this final conclusion about the local convergence. So we assume f is twice differentiable. Okay, and M ellipsis continuous Hansen, and the x star is the local minimizer with a strong curvature. Means at the solution your Hansen has a positive minimize eigenvalue. Okay, then as long as we start the Newton method from a point which is close enough or close to the distance between x0 and the minimizer is upper bounded by this constant, then your sequence will decrease double exponentially, which described by this inequality. Okay, this inequality. The idea of the proof of this theorem was in the last slide. Okay, first you got this. They got this Newton lemma. Okay, you rewrite xk plus 1 minus x star as this matrix minus xk minus x star, and then you get our upper bound of this matrix with respect to normal by the constant times xk minus x star. Then you put these two together, you got the distance decreased double exponentially, which is exactly the conclusion of this theorem with two assumptions. One is your initial point is close enough. Another is your Hansen should be ellipsis continuous, and you have a strong curvature at the solution. Okay, so this is the conclusion about the local convergence of the Newton method. Actually, beyond the local convergence, which means the Newton method converges very fast or much faster than the gradient methods. But on the other hand, we can also have the global convergence. Okay, the global convergence. To get the global convergence, the ellipsis continuity of the Hansen is not enough. We need a even stronger assumption, which is called strong convexity or strongly convex. Okay, we need here we assume the function f is mu strongly convex and L smooth, which this is smooth or this ellipsis continuity is respect to the Hansen, which means your Hansen should be upper bound by mu I and lower bound by Li. Okay, for any x belongs to the Rn. Actually, let's analyze a little bit here. Actually, in the local convergence theorem, we also have something like this. Your Hansen should be upper bound or have the positive minimum eigenvalue. But you need to be careful. This assumption only holds at the solution. But here, this strong curvature assumption holds for any x. So for any point in the whole space, your Hansen should have a unified lower bound. Okay, it means at any point your Hansen should have a positive minimum of the eigenvalue. Okay. Before we go to the proof, let's review a little bit about what is strongly convex function. Okay, so this is a definition. Okay, this is a definition. Of course, we need to assume f is differentiable. If not is differentiable, if f is just convex, you can use the subgradient. You can substitute the gradient by the subgradient. Okay, so the first order characteristic is this. Somehow means your gradient or your subgradient is a strongly monotone operator. Okay, And you will also have a second order characteristic, which means your Hansen is upper bound by a positive constant. Okay, here this mu should be a positive constant for any x. Okay, and we also have a conclusion around the solution x star. You will have a quadratic here. You will have a quadratic growth. Okay, and in the proof, we need to use the definition of the strongly convex function here. So, what is the proof? The idea is like we use the gradient descent lemma first. Okay, in a preconditioned version of the gradient descent method. What does it mean? Actually, if we recall what is the gradient descent method, okay, it's like xk minus some alpha k dk, or alpha k gradient of xk. Okay, so this is gradient descent method. Actually, we can say here there is nothing, but we can also regard it that you have identity here. Okay, so actually this method can be generalized as xk minus alpha times some dk, which is matrix, times the gradient of fk. Okay, in the reference which I mentioned later, this is called the preconditioned gradient descent. Okay, which is much more general than this one. Here, if you choose the dk equals to the inverse of the Hansen matrix at point xk, then you will get the xk equals to xk plus 1 equals to xk minus, okay, we use alpha k here, okay, alpha k, and the inverse of the Hansen times the gradient of xk. Okay, so this is the damped Newton method. Okay, the damped Newton method. So this damped Newton method is just a special case of this scheme, in which you have a more general matrix before the gradient. So we use the gradient descent lemma for this preconditioned version of the gradient descent method. Why we can use this gradient descent lemma? Because you have the Lipschitz continuity of your Hansen. Of course, you have the Lipschitz continuity of your gradient. So you have this is a gradient. This is a descent lemma. Okay, we use descent lemma here, and here we use the. Don't forget, the Hansen has an upper bound, also has a lower bound here. Okay, so we use the upper bound of the Hansen here. Okay, which is related to mu. Okay, because here actually you can have a you can have an identity here. Okay, you can regard it. You have an identity here, and the identity equals to the Hansen times the inverse of the Hansen. Okay, so you get you use the bounded of your Hansen matrix here. You have this first inequality, and then you rewrite this. Okay, you rewrite this with you substitute the xk plus 1 both here and here by the definition of the Newton method. Then you get this one. Okay, then you get this one. fxk, you have the inverse of the Hansen here and the inverse of the Hansen here times the gradient, because we substitute the xk plus 1 by the definition of the stamped Newton method. Okay, and if we assume your step size eta is less than or equals to mu over L, okay, then we have this one. Okay, then we have this inequality. This is immediately from the first inequality. Okay, so remember we already have one direction, okay, one direction which we get from the gradient descent lemma, okay, and with this step size. On the other hand, we use a Strongly convexity, okay. Remember we have recalled the definition of the Strongly convexity. For any y in the whole space, we have this. This is just by the definition of the strong convexity and strong convexity. And this mu is a constant with respect to strongly convexity, okay? And by the same argument you rewrite I equals to the Hansen minus the inverse of the Hansen, and you use the lower bound of your Hansen, okay? You use a lower bound of your inverse, of the inverse of your Hansen, which is the 1 over L, okay? You get this one. So to get this inequality, first you use the strongly convexity, then you use the upper bound and lower bound of Hansen. Of course, you have an upper bound and lower bound of the inverse of your Hansen. And then you minimize both sides of this inequality, okay? Actually, here, you can first fix the y on the right side. Then you minimize the right side, the term on the right side, okay, with respect to y. The idea is the same as we derive the Newton method. We just take the gradient of this term with respect to y and let it equals to 0, okay? And then we minimize the left side of this inequality here. So we get fx star here on the left side, and the right side you have this inequality. This part, how do we get this part? It's just to make the gradient of this part and let it equal 0 and make the solution of y, and then you get this. And this inequality is equivalent to this. So remember, from the strongly convexity we got another inequality. So up to now we have two inequalities. First, if the step size is less than this constant, from the Lipschitz continuity we get this inequality. And on the other hand, from the strongly convexity, we got this inequality. You see, both inequality are related to the function value, okay? So we put this inequality together, okay? We put this inequality together. Then we have this fxk is less than fx minus this constant times fx minus x star, and then by some computation we can have the finally one, which is fxk plus 1 minus fxk is less than, first we get this one, is less than or equals to this constant and times this value, okay, times this value. That's why we need to assume the step size eta is less than mu over L, okay, mu over L. Sorry, I think this should be L over mu, okay. Somehow we need to choose this step size to guarantee this constant should be less than equals to 1. Okay, then your function value will decrease, okay? And if we substitute, if we make assumption of this inequality, and then we can get this fxk, no, if we use this inequality for k times, then we can have this constant to the power of k and times fx1 minus fx star, okay? Finally, we get this global convergence, okay, global convergence. So we say this is our conclusion, okay. If we assume the function is strongly convex and also smooth, L smooth with respect to the Hansen matrix, then the distance to the optimality of the iterates, okay, generated by the adapted Newton method with the step size mu over L decrease exponentially, okay? So this is the rate of the iterates, and this is the rate of the function value, okay, of the function value. And okay, here we got the function value inequality, and together with okay, so here we have this conclusion about the global convergence. Okay, global convergence. Actually, beyond the pure Newton or damped Newton method, we have some modifications. The motivation of modifications because is that the Newton method has some very obvious drawbacks. First, if you use your Newton method here, one of the problem is this may not be defined, okay? Which means your Hansen may not be invertible, okay? And another thing is, to get the convergence, your initial point will be close enough to your solution, but in many times you cannot get immediately a point which is close enough to your solution or which satisfies your assumption which I mentioned above. Okay, so there are several types of modifications. The first is you can combine with the gradient descent method, okay? Sometimes the Newton method may not be well defined or it may not be a descent method. But if you combine with the descent direction, here the ds is the descent direction, gradient descent direction, and the dnk is the Newton direction, then you can get a method which has a global convergence which requires weaker assumptions. Of course, this combination is not unique, okay? And another is, okay, actually the Newton method, as we mentioned before, is, for example, if we delete this diagonal matrix, okay, it's just to solve this nonlinear equation. But sometimes this, if we only have the Hansen here, this may not be invertible. So we plus a positive diagonal matrix to make this matrix is positive definite, okay, or invertible. Then you will get a direction dk which equals to the inverse of this matrix times the gradient. Then you get this new decay, which is the inverse of this positive definite matrix. The inverse of this positive definite matrix is also a positive definite, okay, times the gradient, which can be a descent method, okay? You can prove it easily. And another is regularization, okay? This idea is something similar to the proximal point method for minimize minimize a function, okay? So instead, actually, if we eliminate this cubic term, this is the Newton method, okay? Because the Newton method is just to minimize the quadratic approximation, okay? Of course, we do not have the fxk here, but it doesn't make any difference for these minimization problems, okay? But the pure Newton method without this cubic regularization has a very strong assumptions for the global convergence, okay? It can be used only for very restricted class of functions. But with this kind of cubic regularization, the method can be generalized to much more general functions, okay? So this is another way to improve the Newton method, okay? Because of time, we do not have, we cannot discuss too much about this kind of modifications, but maybe in the future, we will give a class to discuss this kind of modification, especially this kind of regularization is a very interesting work by Nesterov and Polyak, okay? And okay, this is a reference. Many of the materials from this lecture of this nonlinear optimization course from MIT, okay, including the counterexample I mentioned before. Okay, that's all. Muito obrigado.